So what you're looking at here is the sort of compass that a person going on a hike might carry with them along with a map in case the battery runs out on their GPS so that they can find their way back home. The red side of the compass needle is pointing towards north. So we're going to use this to establish which way north is pointing in these demonstrations. So holding that thought in mind that north is pointing to the left of the frame, I'm going to set in here a bar magnet that is on a reasonably low friction pivot here, and you can see, especially if I bounce it a little bit to help break the friction, that the bar magnet wants to align the exact same way that the compass needle did. Now I'm going to go and bring in another bar magnet and we'll see what happens. So you can see if I have two bar magnets close to each other that they attract each other. In fact, as they get too close, they do a really good job of it. Okay, and you can see if I rotate it like this, notice how they're pointing in opposite directions to each other. We've got the blue end, got the red end in my hand pointing to the right, and you can see that the red end and the one that's left to swing free is pointing to the left. Here you can see that the red is attracting the blue, and here you can see that the blue is attracting the red. Now when we let just one compass needle sit, one magnet sit all by itself, we saw that it oriented itself the same way that a magnet would. So this red end is what we call the north-seeking end of the magnet. Now, as we get into the magnetic force, the good first place to start is always to ask yourself, is this a manifestation of some force we've seen before? We can tell that it's not gravity because while we can certainly attract, we can also repel. So it's not gravity since gravity only attracts. So what about the electric force? So I have here is a piece of felt and a PVC rod, and I'm going to go ahead and rub them, and when I do so, the PVC rod will pick up a negative charge. I'm going to hold it near the north end of the bar magnet. I'm going to ask you to predict what, if anything, will happen. Okay, it appears to attract the north end of the magnet. So I'll go ahead and rub it again just to make sure that the PVC rod is nice and negatively charged. And so I want you to predict what would happen if I hold it toward the south end of the magnet, the blue end. Yep, we're attracting it there too. So it turns out that if I put an electric charge near this, it attracts either way. So this can't be the electric force because one end would attract and the other would repel. So the electric force is definitely happening, but it's just the usual thing that we've seen before, that if we bring up a charge to an electrically neutral object, you'll set up a separation of electric charges that will cause an attraction. So that's happening, but that's different from this magnetic force. So with that, let's go ahead and recap what we've seen so far. Okay, so what have we seen so far? Well, so far we've seen that two bar magnets can attract or repel each other. and that the strength of the interaction falls off with distance. We concluded from the fact that not only can you attract, but that you can repel, that this is not gravity. So then we took a look and wondered if it could be the electric force, and the answer there was no. The same electric charge attracted either side of the bar magnet. That's consistent with just good old polarization. So an attraction of a neutral object due to polarization. So to be clear, the electric force was present, but the interaction between the two magnets was not an electric interaction. On top of that, the magnet itself cannot induce an electric polarization if you continue to do some experiments. So I'll just assert that. So we did see an interesting phenomenon, though. We saw that our bar magnets acted like compass needles, and this is really no surprise because our compass needle turns out is just a small magnet. And the behavior that we see where if I put the magnets in a row, they align, but if I put them next to each other, they anti-align. That is consistent with being some sort of a dipole type action here. So we have magnetic dipoles. But we'll have to sit and think about what that might mean. So if we think about that experiment that we just did where we put the magnet on a pedestal, we saw that in the absence of anything else, the end of the magnet that was painted red pointed toward the north, and the end of the magnet that was painted blue pointed toward the south. But actually, I think to avoid potential confusion here, I'm just going to draw the magnet like so. And then I want to be very clear that when we draw like a red N or a blue S, we are just drawing a label on the magnet. And we see that the north end, that this the end of the magnet labeled with the N, that points towards the Earth's north pole. So we call this the north-seeking pole of the magnet. And I'm going to put seeking in parentheses here because nobody ever says it. And similarly, this end here that pointed towards the south, we cleverly call that the south-seeking pole of the magnet. And again, nobody ever says the seeking part. Now, some other workers had done some experiments on magnets where what they did was they took a magnet and they cut it in half. And what they found was that you didn't have like just a separate north and a south just saying all by itself anymore. But instead what you ended up with was two magnets, one with a north and one with the south. And then it turned out that you could go ahead and subdivide it again, and exactly the same thing happens. You just end up with smaller magnets. I mean, the strength of the magnets is decreasing, to be fair, but you always have a north and a south end. And it turns out that we can actually take these subdivisions all the way down to the atomic level. So you can subdivide all the way to an atom or even a piece or even a elementary particle. So subdivide to particles, individual particles. And even at that level, when you're just looking at a single particle, it still has a north end and a south end. So what we're seeing here is that whatever's driving the magnetic interaction, it's a dipole, but it's not made the same way that electric dipoles were. Remember the way that we've seen how to make electric dipoles so far, and it turns out there are other ways. But the way we've seen it so far is you just had a positive and a negative charge with a separation. Here we see dipoles without individual charges, without individual magnetic charges. And all of our best experimental evidence to date we have yet to see a single isolated magnetic charge. Another name for a magnetic charge is a monopole. Monopole. There we go. So we haven't seen any convincing evidence that these monopoles exist. And it's not for lack of searching. And it's not just because, well, gee, it sure seems weird that we can divide atoms, divide a magnet all the way down to constituent atoms. And the atoms are still showing north and south poles, although that's interesting enough. So it turns out that there is a paper due to a famous physicist by the name of Paul Dirac, who came up with a very clever explanation for why it is that electric charges are quantized. That is, that they come in these discrete bundles of E, 1.6 times 10 negative 19 coulombs. And the argument that he makes seems very natural. And it also predicts that if his argument for why electric charge is quantized, it also predicts that there ought to exist isolated magnetic charges. So people have been looking very hard for these. Current best estimates, if they exist, there can't be more than basically a few million of them in the galaxy. And the galaxy is a very, very big place. And if you're saying there's only a few million of them, that's basically like saying that there's zero. So they could be anywhere in the galaxy if they even exist, and they might not. All that is required is that, in fact, is that there exists an odd number of these hypothetical monopoles in the universe. And I'll point out that the number 1 is an odd number and would do the job. Now we know how to modify all of our equations of electricity and magnetism if these beasts are ever found, or if we ever succeed in making one at, say, CERN or someplace like that. But to date, it has never happened. So for our purposes here, we're going to take it that there are no isolated magnetic charges. You can't have a north without a south. They are always together. They're not even a charge, it turns out. It's just a dipole, and one end of it is called north, and the other end is called south. That's how non-existent magnetic charges are. Now, because they do exhibit a dipole behavior, but not an electric dipole, let's go and take a look at our bar magnet kind of zoomed in a bit. So here's our north pole. Here is our south pole here. Associated with the magnet are what are called magnetic field lines. And they look just like you would have seen with a dipole, with an electric dipole, except there are no magnetic charges. And you can see that since there are no magnetic charges, the one big difference that we have versus an electric dipole is that the magnetic field lines just loop on themselves. They don't start or stop anywhere. And this is because to the best of our knowledge, there are no isolated magnetic charges. So there is no place for a magnetic field line to start on or end on. So inside the magnet, magnetic field lines are running from the end painted south to the end painted north, and then outside they loop from the end painted north to the end painted south, but they just go around in a loop like so. I'll introduce it more formally a bit later, but we will say that the magnet has a magnetic dipole moment, mu. And it points along the direction of the magnetic field inside the magnet. Now what we see happen is, say, when I brought in the other bar magnet, or if we use a little compass needle or something like that, if I go stick, say, a little compass needle right here, it'll turn out that what it will do is it will align like so with the north end of the needle there and the south end of the needle there. So what's happening here is its local magnetic moment will point along the magnetic field. So we see that magnets like to align with the local magnetic field. By the way, we can read these field line diagrams the exact same way we would do if it was an electric field. Let's say you go ahead and, if this is your point of interest right here, you go ahead and you draw a vector that is tangent, and the closer packed the lines are together, the stronger the magnetic field. The symbol for magnetic field is the letter B, and as far as I understand it, it was purely chosen because it's the letter that came after A. And then here it's aligned again with the local field lines. But since the field lines here are spaced wider apart, the field strength is weaker. So at every point in space, just like you would have at every point in space an electric field vector associated with that point in space, there is a matching magnetic field vector. Now to get to the point of confusion that exists about these north and south names. And all I can say right now is I am really, really sorry for what's about to happen. Confusingly, there are 3 different Norse that we have to keep track of with the Earth. So I'm going to draw a really bad Earth. I told you it was going to be bad. Jeez, that's bad even for me. Alright, well, I tried really hard. This is supposed to be some really bad version of North America, Latin America. Okay, I tried. Anyway, I do want to draw Brazil a little better, though, so let me do a better job of drawing Brazil. You'll see why in a moment. So the way you locate the geographic North Pole is the Earth rotates on its axis, and the geographic North Pole is where the rotation axis intersects the surface of the Earth. But that's also true down at the geographic South Pole, so how do we pick the two apart? Well, you either imagine the planet is really small or your right hand is really big. And what you do is you grab the planet with your right hand, with the fingers of your right hand curled to match the Earth's rotation. And the way that I remember which way the Earth rotates is the wedge of, is that the wedge of Brazil means spin this way. So I think of the wedge that Brazil makes into the Atlantic Ocean as an arrowhead, meaning spin this way. So if you grab the planet with your right hand, with your fingers curled to match the spin, your thumb points along this axis here, and your thumb defines that this is the geographic North Pole. So that locates the geographic North Pole. Now, as you've probably caught on, the reason that compass needles orient has to do with the Earth's magnetic field. So there is a point on the surface of the Earth, and I'll draw it where it was back in about the 1970s. This location on the surface of the Earth is called magnetic north without the word pole. This is the point on the surface of the Earth that north-seeking compass needles are pointing to. Now it turns out that for the last couple hundred years or so in North America, by sheer coincidence, this point happens to be pretty well lined up. Say if you're here, this point happens to be pretty well lined up with the geographic North Pole. And so your compass needles don't deflect too far off. That's not true in other parts of the Earth. But if you think about it, we saw that when we brought two bar magnets next to each other, there's a north and a south end that got attracted to each other. So this means if we map out the magnetic field lines of the Earth, they are tilted off to the side a bit, but unfortunately I picked kind of a bad view for it. Looking something like this. And so actually in mid-latitude North America, as an example, it turns out that the Earth's magnetic field points mostly down and a little bit to the north. But effectively, if we imagine that we stuck a giant bar magnet inside, that makes this the south end, and that makes this the north end. So this location down in here is the actual magnetic north pole, if we imagine it as, magnetic south pole, if we imagine it as a giant bar magnet. So magnetic north is the point on the surface of the Earth that sits right underneath the magnetic south pole. And this is where the north-seeking compass needle point to. Now, if that weren't confusing enough, where this point is moves with time. It turns out that the mechanism for creating the Earth's magnetic field is that as the Earth rotates, ions inside the molten part of the Earth get dragged around in vortices and wind up acting like an electromagnet. So this giant green dot here is the location of magnetic north, where it was located in 1901. So you can see that, yeah, if you're in the United States and you were east of the Mississippi, in 1901, just by sheer fluke, your compass, this green line here means that your compass needle just happened to point at the geographic North Pole, because the magnetic north and the geographic North Pole up here just happened to be lined up with each other. So in 1901, if you're east of the Mississippi, your compass needle did a pretty good job of pointing to geographic north. And we can go ahead and advance it. So here is 1943. You can see that what's happening is magnetic north is moving a little further to the north. It's still located in the Canadian territory of Nunavut. So for much of the 20th century, where the red end of a compass needle is pointing toward was this location in Nunavut. As time went on, we can see that this is tracking further and further north, although it never quite perfectly hits the geographic North Pole. And then it starts heading off into the Arctic Ocean by the year 2000. Now here I'm going to have to flip to an Arctic map where we are looking. So this is Canada right here. We've got, and this is the magnetic North Pole in 2000. As time continues on, we can see that the location of this is moving, and now, let's back it up just a little bit. In right about these days, we can actually see that, if anything, the magnetic north is now located towards the Eurasian side of the North Pole. So this green dot is still where compass needles point. Now, if you're on the green lines in this map, by sheer fluke, your compass needle happens to also be pointing to geographic north. So again, it's still the case that, for instance, in North America, now it's more like, okay, if you're basically, right around the Mississippi, compass needles pointed to the north, whereas 100 years prior, it was if you were in a line that, say, connected the eastern coast of Lake Michigan down through the center of Florida. So over time, this has moved. And so now, if you lived in, say, this part of the United States, as an example, compass needles are now pointing a little bit west of where the North Pole, the geographic North Pole, actually is. Hikers know this, and in their maps there are little guides for how to correct for the fact that compass needles aren't pointing to the geographic north. Interestingly, in the aviation world, the runway numbers are actually to the nearest 10 degrees with the zero dropped off, the magnetic heading of the runway. So for instance, runway 8 points along 80 degrees, so almost east, a little bit north. And that's within a range of plus or minus 5 degrees. Now, every so often, what will happen is as magnetic north moves along, they actually have to renumber the runways because the and add or subtract 1 to the runway number to take into account the fact that the compass needles aren't pointing where they used to anymore when the runway was built. Alrighty, so I will finish off this video with just one bit of convention that we're going to need, because it turns out that with magnetism, everything is going to be very fundamentally three-dimensional. And so if you've ever had any organic chemistry and you've run into wedge and dash, physicists don't use wedge and dash, but we have our own ideas like this. So let's say you are drawing a field lines. If you have a whole collection of magnetic field lines that are going into the screen, what you do is you just draw a bunch of X's. And if they're going out of the screen, you draw a bunch of dots. So you can think of this as the feathers of arrows flying away from you and the points of arrows flying toward you. Now, if you are dealing with vectors or currents, what the convention is then is you just draw a single X in a circle or a single dot in a circle. So the fact that you drew a whole bunch of these, you should be thinking of lines going in and out of the screen, or sorry, going into the screen here, and here going out of the screen. Here, this would be a single vector arrow going into the screen. Again, the X represents the feathers of the arrow flying away from you. Here the dot represents the point of the arrow flying toward you. So in the next video series, we will go ahead and introduce the magnetic force and take it from there. So catch you over there.